Good morning, everyone. Myself, Dr. S. Devikala, Associate Professor in the Department of Chemistry, SRM Institute of Science and Technology. In today's class, let us see about coordination chemistry in detail. So, the complexes are said to be colored. For example, Prussian blue. Early well-known coordination complex which include Prussian blue only. Early contribution by Swedish mineralogist and chemist Christian Wilhelm Wormstad and Danish chemist Sophus Medas Jorsen. It was not until 1893 the most widely accepted version of theory today was published by Alfred Werner, that is the Nobel Prize winner in chemistry in 1913. Prussian blue is used as a pigment in the girl's dress, Mary's veil, and in the sky. So according to Werner's theory, there are two types of valencies, namely primary valency and secondary valency. Primary valency, it corresponds to oxidation state of the metal ion, whereas secondary valency corresponds to the coordination number. Primary valency, it is ionizable, whereas secondary valency, non-ionizable. Coordination number, that is equal to the number of ligands. Generally, coordination number of a complex can be calculated by knowing the number of ligands. So ligands are nothing but it may be neutral molecule or it may be polar molecule, or it must have at least lone pair of electrons to interact with the metal. Let us see several coordination number with respect to some examples. So based on the coordination number, if the two ligands are bonded to the attached to the or coordinated to the central metal ion, then the geometry or the structure is said to be linear. If it is 3, trigonal planar. If it is 4, tetrahedral or square planar. If it is 5, square pyramidal, trigonal bipyramidal. If it is 6, octahedral. In some cases, it may be trigonal prismatic. You can skip this slide. Coordination number 7, higher coordination number mostly occur with the complex of lanthanides. Pentagonal bipyramidal, capped octahedral, monocapped trigonal prismatic. If the coordination number is 6, cubic, square antiprismatic, dodecahedral. If it is 9, some of the examples given over here, it's also in case of lanthanides and actinides only. Tricapped trigonal prismatic. If the coordination number is 12, then it is icosahedron. It is a polyhedron with 20 faces. So ligands, you have different types of ligands. Here you can see chelating ligands and chelate complexes. When a bidentate ligand binds to a metal, it leads to chelate. You can see the structure over here. These are some of the bidentate bridging ligands. For example, pyroxene. The middle ligand is a bidentate ligand, but it bridges two metal centers but does not chelate. Some of the metal EDTA complex well known, ethylene diamine tetraacetate. It is abbreviated as EDTA. It has 6 donor atoms. It wraps around the central atom like an octopus. So what is chelate effect? Metal complexes of polydentate ligands are more stable than complexes of chemically similar monodentate ligands. So EDTA is used as ligand in complexometric titration. Next we move on to isomerism in coordination compounds. Isomers, generally we know very well, compounds with same molecular formula but different structural arrangement. Based on the structural arrangement, they are classified as structural isomers, or based on the spatial arrangement means they are termed as stereoisomers. So this flowchart tells about the further classification of isomers: structural, stereo. Under structural, you have ionization, hydrate, coordination or coordinate, linkage. Under stereo isomers, you have geometrical and optical. So structural isomerism, ionization, hydrate, coordinate and linkage. In case of ionization, same formula, molecular formula, it will be the same, but they will give different ions in solution, so that they are termed as ionization. So if you see on the left hand side, you can find Br minus ions, whereas right side complex, it will give sulfate ions in solution, so that they are termed as ionization isomers. Whereas in case of hydrate or solvate, so generally water acts as a solvent. So based on the number, depending on the number of H2O molecules outside the coordination sphere, accordingly the isomerism is termed as hydrate or solvate. Then the next one is coordinate isomerism or coordination isomerism. Here in the left hand side complex, amine ligand is attached to cobalt central metal ion, whereas in the second case, cyano ligand is attached to Cr. So here the ligands vary, so that they are termed as coordinate or coordination isomerism. But they have different complex entities, that is complex ions. One more example with respect to zinc and copper. So linkage, in case of linkage isomerism, composition of the complex ion is same, but the point of attachment of at least one of the ligand differs. If you see here, the central metal ion is cobalt here. Cobalt is bonded directly, nitrogen is directly attached to cobalt. Whereas if you see to the right side, oxygen is directly attached to cobalt metal ion. So same ligand, but the donor atom is different. If the donor atom is different, then it is called as linkage isomerism. Which atom is linked to the central metal ion? So here in this case, left side, the complex color of the complex is violet, whereas here it is orange. Here the ligand is, the linked atom is sulfur. Sulfur is directly attached to cobalt, whereas here nitrogen is directly attached to cobalt. One is thiocyanate, the other one is isothiocyanate. The linkage of the element that is present in the ligand that varies. So let us move on to geometrical isomers. So geometrical isomers are most important for square planar and octahedral complex. Here you can see some of the square planar complexes. All the vertices of a square are equivalent. It does not matter which vertex is occupied by ligand B in a square planar Ma3P complex. Here Ma3P complex, that is the representation of the complex. That is coordination number is 4, no? So central metal ion is bonded to 4 ligands totally. A3, that means 3 3 plus 1 totally 4. Only one geometrical isomer is possible. For Ma to B2 square planar complex, there are other possible arrangement also, cis form as well as transform. So in this slide, you can see cisplatin and transplatin. Cis isomers have like groups on the same like groups on the same side, whereas trans isomers have like groups on the opposite side. Same groups are on the same side. This, as you all know very well, whereas if the same groups, if they lie in the alternating position, means it is trans. Number of each atom is same. The mode of bonding also same, but the arrangement in space is different. That's what I told you now. If the like groups are on the same side, then it is cis, opposite side trans. So here cisplatin is used to treat various types of cancers, whereas transform does not exhibit comparably useful pharmacological effect. Next, let us see isomerism in case of octahedral complex. Octahedral complex, one representation Ma5B. So if two ligands in an octahedral complex are different from other four, then two isomers are possible, that is cis and trans isomers. So in terms of color, in this slide, it is differentiated, red form and green form. Again, this slide also, it tells about the isomerism in octahedral complexes only. Then let us move on to stereoisomerism. Under stereoisomerism, you have optical isomerism. So isomers have opposite effects on plane polarized light. So the ability of a substance to rotate the plane polarized light, it is called as optical activity. Generally, molecules that have non-superimposable mirror images. If I say non-superimposable mirror images means it refers to chiral molecules. A chiral carbon is one. Carbon, we all know, valency of carbon is 4. If the carbon is bonded to 4 different groups or functional groups, then it is called as chiral carbon. Generally, it is denoted by asterisk mark, that is star. What type of compounds are said to be optically active means the criteria or the condition that is required is it must have at least one chiral carbon. So in general, enantiomers means isomers of non-superimposable mirror images. So if you see here, your human hand exhibit a non-superimposable mirror image. Just as your right hand will not fit into your left thumb. Two enantiomers cannot be superimposed on each other. If they are completely superimposable, then they are optically inactive. Next, let us see what is PPL, that is plane polarized light. Ordinary light that can be reflected in all directions, that is called ordinary light. Whereas plane polarized means the deflection is with respect to any one of the plane, that is single plane only. That is called that is the difference between ordinary light and plane polarized light. Next, let us move on to the concept of enantiomers. Enantiomers are non-superimposable object and mirror images. This is the simplest statement in order to define enantiomer. I'll repeat. Non-superimposable object and mirror images are termed as enantiomers. So if you see the properties of enantiomers, all the properties it will be the same. They differ only in the rotation of PPL, that is plane polarized light. All its boiling point, freezing point, density, melting point, everything it will be the same, but they differ only in the plane polarized light rotation. That is, if one compound, if one isomer is going to rotate the plane polarized light in the clockwise direction, means the other form it will rotate the plane polarized light in the anti-clockwise. So that one form is called as dextro, the other form is called as levorotatory. So two enantiomers rotate the plane of polarized light equal in opposite direction. Opposite direction, it is nothing but plus and minus rotation. That is dextro and levo. If one enantiomer rotates the light 30° to the right, the other will rotate it 30° to the left. This is the simplest version. Next, we must know what is racemic mixture or racemate. It is the equimolar proportion of D and L form, or in other words, equal mixture of two enantiomer, that is 50:50 ratio. It is called as racemic mixture. The rotation of plane polarized light by a racemic mixture is 0. Why it is 0? The plus rotation, one form, if it rotates the optical plane polarized light in the clockwise, means the other one in the anti-clockwise direction, so that the overall rotation is said to be nullified, so that it is 0. So one example is given over here, that is En stands for ethylene diamine. This is the structure of ethylene diamine. Plus COEN twice Cl2. Cl exhibit geometrical isomerism? The answer is yes. Trans and cis isomers. Does it exhibit optical isomerism? Only cis form yes, trans form no. The reason these two forms are identical, that is superimposable. So only one trans isomer possible, so it is optically inactive. Whereas the two enantiomers of the cis form optically active. That means they are non-superimposable. So two enantiomers are cis form. These two forms are non-superimposable. So I'll repeat it again. In order to be optically active, it must have non-superimposable object and mirror images. Here are some more examples of octahedral chiral complex. We can skip this. Let us move on to the theories of coordination compounds. Several theories was proposed by several well-known scientists: valence bond theory, crystal field theory, and ligand field theory. Ligand field theory is also called as MOT, well-known MOT, that is molecular orbital theory. So in this valence bond theory, this theory it is used to explain the geometry and magnetic property of many coordination compounds. The basic idea of the theory is that the formation of a complex is a reaction between a Lewis base, that is generally a ligand. Ligands are nothing but electron donor, whereas Lewis acid, metal or metal ion, generally metal or metal ion, it will accept electron, so electron acceptors with the formation of coordinate covalent bond. The coordinate covalent bond, it is also termed as dative bond, that is the bond between the ligand and the metal. It is based on the following assumption. Let us see the assumptions one by one. So the first assumption is that the central metal atom or ion, it provides number of vacant sp d orbitals equal to its coordination number to form coordinate bond with the ligand orbital. Each ligand has at least one sigma orbital containing a lone pair of electrons. And then the third assumption, the empty orbitals of the metal atom or ion undergo hybridization to form same number of hybrid orbitals. These hybrid orbitals can overlap with the filled sigma orbitals of the ligands to form ligand to metal coordinate sigma bond. Finally, the fourth assumption, the geometry of the complex ion depends on hybridization of metal orbitals. It is usually possible to predict the geometry of a complex from the knowledge of its magnetic behavior on the basis of VBT theory, that is valence bond theory. The important limitation, it has failed to explain or the differentiate between the structural and magnetic properties, and it fails to explain low spin and low spin square planar and high spin tetrahedral and high spin octahedral complexes. So some of the disadvantages, drawbacks or demerits of VBT, it includes it fails to predict whether a 4-coordinate complex will be tetrahedral or square planar, and whether an octahedral complex will be low spin or high spin. It fails to distinguish certain geometries like tetragonal or distorted octahedral. It completely neglects excited states in a complex and cannot explain absorption spectrum. It does not have scope for quantitative calculation of bond energy and stability of complexes. It does not adequately explain the magnetic data beyond specifying the number of unpaired electrons. Too much attention has been given on metal ion, whereas the importance of ligand is not at all properly addressed. So in whatever the shortcoming we have in VBT, the next theory, crystal field theory, that was proposed. So it talks about the stability, magnetic behavior, color, hydration enthalpy, structures, and so on. Why it is termed as crystal field theory means it generally applied to any ionic crystals. Here in this case, in this crystal field theory, it is also called as ligand field theory. Here the ligands are considered as point charges or point dipoles. Point charges means it may be negative or positive ligand, whereas point dipole, it refers to neutral molecule. So in case of any gaseous metal ion, all the 5 d orbitals are said to be degenerate. We know the word degenerate means orbitals having same energy. So in this slide, you can see the shapes of 5 d orbital. As we know, we have d orbitals 5 types: dxy, yz, zx, zx square minus y square, and dz square. So you have axial and non-axial orbitals. So d orbitals are further classified into two types: axial orbitals and non-axial orbitals. So orbitals are said to be affected when ligands approach a metal in an octahedral arrangement. So in case of octahedral arrangement, the central metal ion, it occupies the center of the octahedron, whereas the 6 ligands occupies the corners of 6 corners of octahedron. Initially, when the ligands approach the central metal ion, the degeneracy is said to be maintained. Based on the nature of the orbital, that is whether it is axial or non-axial, accordingly the degeneracy is said to be lost. As a result, that leads to splitting of d orbitals into two types. One is lower energy, the other one is higher energy orbital. So in this slide, you can see ligands with a pair of electrons approach to the metal along x, y, and z axis for an octahedral complex. This state is called as barycenter. The average energy is said to be 0. Based on the nature of axial and non-axial orbital. Axial orbital means generally it will lie exactly along the axis, whereas non-axial orbital in between the axis. Since the lobes of the ligands and the lobes of central metal ion, there is a chance for these two lobes being closer together, so more repulsion. As a result, the T2G orbital, it takes the lowest position, whereas the EG orbital, it goes to the higher energy state. That is what given here. D orbitals not pointing directly x, y, and z axis are stabilized to maintain overall energy, whereas the d orbitals having lobes pointing directly at x, y, and z axis are repelled most by electron-electron repulsion. The repulsion is more, that's why the splitting occurs here. The same thing it is given over here. So in terms of crystal field energy, you can see here free metal ion in the presence of approaching ligand. This is called a spherically symmetrical or spherical charge field. Whereas in the presence of approaching ligand, it is divided into two, T2G and EG. Here T2G is called as triply degenerate, EG is called as doubly degenerate. So T2G pointing between the ligands, whereas EG pointing at the ligands. The lobes lie directly along the axis. Since they lie directly along the axis, more repulsion between the electrons of ligands and the electrons of metal ion. More repulsion, so the energy is high. Again, the same thing, the crystal field effect on octahedral complex. So the energy gap between Eg and T2G, it is called as crystal field splitting energy, and it is denoted by delta naught or delta oct or 10 dq, where delta represents crystal field splitting energy. This O circle, no, it is representing octahedral. If it is T means it is tetrahedral. Because the overall energy is maintained, the energy of the three T2G orbitals are lower or stabilized by 0.4 delta naught, that is equivalent to 4 dq, and the energy of the two EG orbitals are raised or repelled by 0.6 delta naught, 6 dq, with respect to hypothetical, that is the spherical crystal field or barycenter. This is in terms of absorption spectrum. Next, let us move on to crystal field splitting in case of tetrahedral complex. First of all, you must know what is tetrahedral complex. In a tetrahedral crystal field, we have to imagine like this. That is the 4 ligands lying at alternating corners of a cube. You can see 4 ligands. So here dx square minus y square and dz square. These orbitals are at the center of the cube, which lie between the ligands, and the dxy, yz and zx orbital point towards the ligand. As a result, the splitting observed in tetrahedral field is opposite to that of the splitting in the octahedral complex. So in octahedral complex, what we have seen, T2G that occupies the lower energy state, whereas EG higher energy. Whereas in tetrahedral, exactly the reverse case. EG lower energy state and T2G higher energy state. The reverse diagram you have to draw. So here, because a tetrahedral complex has fewer ligands, the magnitude of the splitting is smaller. The difference between the energies of T2G and EG orbitals in a tetrahedral, as I told you already. If it is tetrahedral, means we have to represent by delta T. Earlier for octahedral, we have represented by delta 0. It is slightly less than half of the splitting octahedral complex. So delta T is equal to, this expression you have to remember, delta T is equal to 4 by 9 delta naught. Again the same thing, comparison octahedral and tetrahedral. In case of octahedral, left hand side what you have is octahedral splitting. So T2G, EG, whereas for tetrahedral it is EG, T2G. And then this relationship also. So when to expect tetrahedral geometry? If the ligands are large, so as to avoid ligand-ligand repulsion. In case of metal ions with 0 CFSC, CFSC crystal field stabilization energy. When do you have 0 CFSC means the fully filled or completely filled electronic configuration. For example, D10, D5. That is in case of MnO4 minus, D10, FeCl4 minus, D5. That is high spin. Then ZnCl42 minus, D10. So in case of metal ions with a small crystal field stabilization energy for 2 electronic configurations, namely D2 and D7, for example, cobalt complex COCl42 minus D7, and tetrahedral splitting is seldom large enough to result in pairing of electrons. As a result, low spin tetrahedral complexes are not common. Rare example is this one, chromium complex. Let us see what are all the factors that affects the value, the magnitude of delta. First one, higher oxidation state of the metal atom. If the oxidation state of the metal atom is high, then delta value is also high. In groups, heavier analog have larger delta. For example, hexamine complexes. You have to remember this sequence. 5D is greater than 4D with xanthan greater than 3D. Geometry of the metal coordination unit, it affects delta value to a greater amount. And then ligands can be arranged in a spectrochemical series according to their ability to increase delta at a given metal center. Let us see what do you mean by spectrochemical series in terms of increasing delta. So it is a series in which the ligands are arranged with the increasing order of splitting energy. Whatever ligands you have on the left hand side, they are termed as weak field ligand, whereas strong field ligand, it includes carbonyl, cyano, amine, triphenylphosphine, and so on. So different ligands on same metal, but it gives different color. So addition of amine ligand to CuH2O6 time, it changes its color. You can see the difference. The blue color, it becomes intense. Then CFSC, with respect to, based on the spectrochemical series, we can predict whether we will end up with high spin or low spin complexes based on the arrangement of the electronic configuration. starting from D1 to D10 arrangement. So metal ions with the D4, D5, D6 or D7, they can be either high spin or low spin depending on the magnitude of delta naught. See, so here you can see chromium 2 plus, Mn 2 plus, all these things. You have 4, 5, 6 and 7. Okay, more number of unpaired electrons means high spin. Less number of unpaired electrons means it is low spin. So large delta naught then will end up with low spin complex. Smaller delta naught will end up with high spin complex. As energy difference increases, electron configuration also changes. We have to see to this number of unpaired electron. If the number of unpaired electron is 0, then it is termed as low spin. If the number of unpaired electron is more, then the complex is termed as high spin complex. Next term will be using pairing energy. It is denoted by capital P. In order to force an electron to pair with another, an energy called pairing energy has to be invested. So this is made up of two terms, Coulombic repulsion and the loss of exchange energy. If the pairing energy is greater than delta naught, then the field is weak field or high spin. If delta naught is greater than P, then it is strong field or low spin. So the nomenclature high and low spin arises from the magnetic moment difference between two configurations. So delta naught greater than P, it is low spin. Delta naught less than P, then it is high spin complex. Again the same explanation only. Here you can see D1 to D10, how the electronic configuration will be, number of unpaired electrons, and then we have to calculate the crystal field stabilization energy, both for weak field as well as strong field. D1 to D3, there won't be any change. Even for D4, the configuration differs only from D5. So in case of square planar complexes also, that is by removing the Z electron gradually away from the metal and finally completely removing it to infinitely apart. Sorry. Next we will see magnetic properties of metal complexes. So we have to remember this formula, the spin only formula, mu effective or mu s is equal to square root of n into n plus 2, where n is number of unpaired electrons. So generally magnetism is caused by moving charged electrical particle introduced by Faraday in 1830s. These particles can be the current of electrons through an electric wire or the movement of charged particles. Charged particle, as we know, protons and electrons within an atom. These charged particles move like planets in a solar system. So nucleus spin around its own axis, it causing a very weak magnetic field. Electron orbit around the nucleus, it causing a weak magnetic field, whereas electron spin around their own axis, it causes a significant magnetic field. The same expression in terms of S also can be given square root of 4s into s plus 1, where s is equal to n by 2. N is number of unpaired electrons. So in this slide, you can calculate the mu s value for different metal ions, starting from calcium till gallium 3 plus. Here in the second column, you can see the electronic configuration, the value calculated, and the value observed, actual value observed. So in terms of color, tetrahedral complex blue in color, whereas octahedral complex pink in color. White tetrahedral complex blue in color because of the magnetic moment value. Here it is 3.73, whereas here it is 4.2. Not only that, based on the number of unpaired electrons. Here you can see 3, here you have 2. So the number of unpaired electron is 3. In both the cases, it is 3 only, but the observed magnetic moment is due to orbital contribution. Then the next one, spin and spin orbital contribution to mu effective. So here the electrons are spinning, creating an electric current and hence a magnetic field. Then the orbital contribution also we have to take into account. Electrons move from one orbital to another, creating a current and hence a magnetic field. So both the spinning of electrons, both the contribution we have to take into account, spin contribution as well as orbital contribution. So the temperature dependence, the slide. So low spin and high spin. Accordingly, the color of the complex varies. Then the next concept is ferromagnetism. In a normal paramagnetic material, the atoms containing the unpaired electrons are magnetically dilute, and so the unpaired electron in one form are not aligned with those in the other atoms. In case of ferromagnetic materials such as metallic iron or iron oxides, for example magnetite, that is well known Fe3O4, where the paramagnetic ion atoms are very close together, they can create an internal magnetic field strong enough that all the centers remain aligned. So in case of Fe, if you see Fe, FeH2O, this complex is paramagnetic, whereas the other one is ferromagnetic. So in case of paramagnetic and ferromagnetic, in both the cases you have unpaired electrons, but here unpaired electrons oriented randomly, whereas here the unpaired electrons aligned in their own common magnetic field. Whereas antiferromagnetism, electron spins in opposite direction in alternate metal atoms. That is called as antiferromagnetism. Then let us see about charge transfer complexes based on the color. Potassium permanganate, here it is chromate, whereas it is chlorate. Let us see some of the advantages and disadvantages of crystal field theory. So the advantages mainly it includes, it explains color of the complex, magnetic properties, it classifies ligands as weak and strong, it explains the difference in physical properties of metal complex, and it explains very well about the distortion in shape observed for some metal complexes. Some of the disadvantages it includes, it does not explain why CO, although neutral, it is a very strong ligand. It cannot predict the shape of complexes. And then charge transfer spectra, it is explained only by CFT. Okay. Here some of the problem also it is given to you to work it out. So cobalt form three complexes. Let us see one by one. Three octahedral complex, COCl6 4 minus, COR2 NCS2 thrice, and COCN 5 times H2O 3 minus. These have magnetic moments 0. That is the first complex magnetic moment is 0. For the second complex it is 1.73, and for the third complex it is 3.9 Bohr magneton. Assign the moments to the complex and predict the relative strength of dithiocarbamate ligand. The formula that can be used is μs is equal to square root of n plus 2, where n is number of unpaired electrons. The solution also it is given over here. Why it is 3.9 means it is weak field ligand, high spin, 3 unpaired electron. Whereas for cyano ligand, it is strong field ligand, low spin, 1 unpaired electron. Whereas for the third one, it is strong field, higher oxidation number, so that it is 0. That's to test. Some more examples. Just we will have a glance with answers. In terms of magnetic moment, based on spectrochemical series, based on the value of magnetic moment. some part of multiple choice questions with the answers for your understanding. So I thank you all for your kind attention. I hope you have understood the topic coordination chemistry. Thank you all.